So as we have seen that the synchronous machine is having a three-phase supply to the stator, and this stator actually is, I can have this three-phase supply in such a way, not this way. I can have this three-phase supply with this current, and I can have my synchronous machine here like this, and this synchronous machine is actually coupled to a DC generator, which is actually mounted on the shaft only. So I can remove this shaft right now, and I can have this shaft over here, and I can have the field windings separately over here. Which is generator, which is a DC generator mounted on the shaft of the machine, and I have the field current IF flowing over in the DC generator, and this DC generator will be producing a phi, which will be actually generating my rotor MMF, or I can say the rotor will become the electromagnet. So since there will be a generated here, the generator E will be there, EMF will be generated, that's why I will be generated, then the flux phi will be generated. Or this, I can remove this flux phi right now, because this is giving the electromagnets, this is becoming the electromagnets. So now coming to the discussion that since the current I will be flowing here, and since this three-phase stator winding is having some reactance, the stator reactance XS over here, and the current is flowing after that I. Back EMF will also be generated, as we have seen in DC machine also, that back EMF will be generated, that is EB, and in there we have seen this is my 3-5 supply. So I can say one more thing, that since the EF back EMF EB, we know that is directly proportional to NS into phi, as we have already seen this relationship in DC machine also, that EB, the back EMF, is directly proportional to your speed phi and NS. Now since this NS is constant, so I can say that back EMF EB is directly proportional to the flux. Which flux? The flux produced by this phi. So if by decreasing my flux phi or by increasing my flux phi, I can decrease my EB, that is the back EMF. And what is the use of decreasing my phi? We will see that. Consider that the rotor or my stator MMF is moving like this, and my rotor, which is over here, since my stator is moving at the speed of ns, but obvious my rotor will also be moving at the same speed ns. So since phi is moving with ns, the rotor is also moving with ns. So the rotor EMF which is getting produced will also be in phase with the stator MMF. So the current which will be the current will also be in phase with that. So I can have one thing that rather than writing over here, this is the E which is this E. So this E will be in phase with this EB which is getting produced here. E and EB will be in phase. So at no load, this E and EB will be here and E and EB will be equal. E and EB will be equal. So I can say that this is the condition when I is equals to 0. So at no load, E and EB are equal. When the load increases, the current starts going up, and at that time, suppose this is my E, I can have a smaller EB at that time. So the minus E minus EB will be smaller than this, again approximately this much. E minus this will be E minus EB. So the current, since this act because of this access, the reactance, we know that the inductance on coil, the current lag the voltage. So current will be exactly 90 degree behind my EB. So first condition what we have seen that E and EB were equal and they were in phase at that time. So there was no current and this was E and EB. In the second case what we have seen that E is greater than EB and at that time E minus EB would be less than the EB and from that I current is lagging by 90 degree. In the third case, if I am able to increase the EB by increasing the phi, so I can have this as EB and I can have E over here. So at that point my E minus EB will be in the negative direction. This would be E minus EB. I can write this relationship here over here, E minus EB. So the current would be lagging behind E minus EB by 90 degree again. So this would be my current I. So I can have one very important, very strong relationship about the synchronous motor is that by increasing or decreasing the EB, I can actually increase or decrease the power factor of the machine. That is, since here power factor is lagging by 90 degree, here the power factor is actually leading by 90 degree. If you can see, power factor is leading out in this case. In this case, it is leading. In this case, it is lagging. So by merely increasing or decreasing EB, which is the function of phi, I can increase and decrease my power factor accordingly. I can, so this, since we have already knowing this fact that the synchronous machine are normally capped on low load in some industrial areas, such to have the power factor correction. So this is the reason that by increasing or decreasing the phi, we will increase or decrease the EB and thereby increasing or decreasing the angle between the E and I, which is clearly shown over here. So I can have an arrangement such that the current which will be leading in this case where my machine is overexcited when EB is there.